So let's warm up, right? So let U be a vector 3, 2. So it's a two-dimensional problem, so that's good. That should make things easier. V is the vector 2, 1. Given that vector W satisfies, if I project W onto U, I get U. And if I project W onto V, I get V. Then what is W? All right, and there's some options here. 5, negative 1, negative 1, 7, 5, negative 3, negative 3, 11, or no such W exists. Do we have an answer? See a hand up? D. Negative 3, 11? Okay. All right. I don't remember, but I'll box it because I have faith that you wouldn't mislead me. Now, there's a couple of ways to do this problem. May I ask, what was your approach to the problem?
Yeah, sure. So first I kind of just used the projection formula.
Okay.
Once I figured out where I need W to be, I just used variables x and y and kind of just solve from there to get a system of equations. You get two equations, one from each projection, and you can solve for W from there.
Nice. Okay. So the approach was, let's not pretend like it's a multiple choice problem. Let's just solve it, which is perfectly fine. And okay, so you said, what is W? Well, let's give W some names. It's something. It's a two-dimensional vector, AB. So it's okay. So here was the outline that was given. We're going to use these projection formulas to get some equations that A and B must satisfy. Now, if you look at the projection formula for W onto U, it looks like U dot W over U dot U times U. So that's the projection of W onto U. We're told that this is equal to U. Well, if that's equal to U, what must be true about this coefficient? It has to equal 1. Okay. So in particular, this tells us we have a formula. We can get that U dot W is U dot U. And we take these dot products. So we have 3A, 2B, and then U dot U is 3 times 3 is 9, 2 times 2 is 4. So 3A plus 2B is 13. That's one equation. Now, that idea is so nice, we do it twice. We just do it here. It's the same thing. We're just changing U's for V's. So V dot W over V dot V times V, that's projection of W onto V, is V. And then we're like, I wonder what that could mean. Well, again, the coefficient has to be 1. So, okay, well now we get another formula. So we get that V dot W is V dot V. And we say, all right, well, V dot W, so that's 2A plus B, and then V dot V is 2 squared, 4, plus 1 squared, 1. So now 3A plus 2B equals 13, and 2A plus B equals 5. 2 equations, 2 unknowns. The bread and butter of calculus. And you'll see that again and again and again. Now there's a couple ways to do this. I like to do elimination. I pick something to eliminate, let's say the B's. I say, well, how can I eliminate the B's? Well, I have 2B, and I say, well, let's make this not 2B. So we'll multiply by negative 2. Because if we do that, 2B minus 2B, no more B's. 3A minus 4A, because right, minus 2 times 2A, makes minus A. 13 minus 10. Well, that's 3. So negative A equals 3, or A equals negative 3, which we can now rule out the first 3. So those I have A equals negative 3. And pick a formula, any formula, and what do you get? Well, let's say we pick the second formula. 2 times A is negative 6, plus B equals 5. Add 6 to both sides, b equals 11. And we're like, yes, good. So it does exist, so that rules out e. All right, so that was a great way to do it. Are there other ways? Anybody else try something slightly different? Just want to point out there are other strategies. So one thing you can do is on a multiple choice problem, you don't have to actually derive an answer. You can say, look, I don't know how to derive an answer, but I do know how to do projection formula. So what you can do is you can just start plugging in the projections. Test A. Does it work? Yes or no? No. Test B. Does this work? No. Does this work? No. Does this work? Yes. Okay, what about here? Yes. Done. So you can test. And that's one of the things about multiple choice. We don't really care how you get the right answer. So you can solve the problem, but you can also say, all I have to do is just verify that one of these is correct. And so whatever you do is fine. I will point out one other way to go about this problem. Just for fun. I haven't tried this yet. I hope this doesn't blow up in my face. But, well, if it does, at least we had fun. Okay, so I am going to think about this vector, let's say 3, 2. So that says you go a change of 3 in the x direction and a change of 2 in the y direction. So there's the vector 3, 2. And I'm told I'm looking for a vector so that the projection onto that is the same vector, 3, 2. Can we describe all such vectors? Well, it turns out you can. So what you do is you make a little right angle here, and you form a line. Now, any vector that goes from the origin to that line, when you do the projection, what will happen? You're going to project, because you're projecting in the direction of this right angle. You will get that vector out. So, this line here, your vector, whatever the answer is, has to go from the origin to that line. But what else do we have? We have a second vector. So that's at 2, 1. Now, unfortunately, now I'm really regretting this because they're very close. Well, now what do? Well, you draw the same thing. You're going to be perpendicular. And if you do that, you get something like this. So again, anything that points to that line, that vector that goes to somewhere on that line, that will project and get back to where you started. So your vector has to start from the origin and go to the green line, and has to start from the origin and go to the blue line. So what are you looking for? The intersection, which is at -3, 11. It works in theory. In practice, your picture has to be really good. But there's a lot of underlying geometrical ideas. And it's fun to think about these. At least I have fun thinking about these. All right, any questions about our warm-up problem?
So then would we have to derive the equation of each of those lines and find the intersection? Or?
Well, again, if you were doing this geometrically, you probably would just look at where they intersect by coordinate axis. You'd actually have something. And it's, like I said, this is not very practical, but it works. And that's okay. You don't have to be practical to have fun. I mean, a lot of things are impractical, but fun. All right. Well, where are we going? First, of course, thought for the day from engineer turned writer Andy Weir. We used to work at NASA. Now he writes books like The Martian. And he says in one of his books, thing is, when stupid ideas work, they become genius ideas. And maybe instead of the word stupid, let's use simple. When simple ideas work, they become genius ideas. A lot of math is based off of simple ideas. And sometimes we try to overcomplicate things. And I will say, one of the things I'm most proud of, and I can't go into too many details for various reasons, non-disclosure type things. But one summer I was working on a project, and we had all these really smart people. I can justifiably say I was the stupidest person in the building, because they were ridiculously smart people. Lots of fun to work with. Great people. And we were working on impossible problems, because that's what we had to do. We had to solve impossible problems. And I remember at the very end, I said, have we tried this really simple idea? And it worked really well. And I thought, we should have found this at the beginning, because it's such an easy thing to do. Never underestimate a simple idea. You might say, well, surely it's been done before. But surprisingly, a lot of really nice ideas have not been tried. So, all right. What's our goal for today? We're going to talk about cross product. So, we're going to talk about what that is, but our goal is to say we're going to take a vector, cross another vector, and out comes a vector. And this is the rule, but we'll talk about how we get there. Don't worry about it yet. I will say, unfortunately, you do have to memorize this part. Now, there is one catch to the cross product. It only works in 3 dimensions. Doesn't work in 2 dimensions. Doesn't work in 4 dimensions. You have to have 3 dimensions. And I'll go ahead and tell you why. It's a very technical reason. So why does it work in 3 dimensions? It's because 3 is equal to 2 plus 1. That's the reason why. Now you might say that doesn't seem like a very technical reason, but essentially the idea, where is the 2 coming from? You have your 2 initial vectors. The 1 is your output vector. And the problem is you have to have something that makes sense. So if you have too many dimensions, you have too many possible outcomes. Too few dimensions, you don't have enough. So you need something that's just right. So that's why it works in dimension 3. It has very nice properties when it comes to direction. So it's going to be our build a perpendicular tool. That's the cross product. Also has some nice applications when it comes to magnitude. So it's related to area of parallelograms, as well as to volumes of parallelepipeds. And I will point out that if you go to your formula sheet, that is on your formula sheet. So the area of a parallelogram is the magnitude of a cross product, which is the magnitude of u, magnitude of v sine theta. And then if you want the volume of a parallelepiped, think box. So you may see the word box product. It comes from a dot product times a cross product, and then you take the absolute value. All right, so that's where we're going. It will be a fun day. All right, so the punchline is we actually get 3 vector products. We've already talked about 2 of them. One of them we may not have really called a vector product, but it's good to think about it that way in context of what we'll do in the future. So that's a scalar product. So scalar is just a fun way of saying number. So a scalar product is I'm scaling the vector. So as I'm taking a constant in the front times a vector, what can I do? Well, I'm either making it longer or shorter, essentially, is what's going on. Why is this helpful? Well, it relates to parallel vectors. Vectors are parallel if they're multiples of each other. Now you can check if vectors are parallel, but you can also use the fact that vectors are parallel. The other big thing that we use the scalar product for is to make unit vectors. And that's important because that is how we describe direction. So in the future, when we need ways to describe direction, we need to pull out our unit vectors. Okay, that was our scalar product. Number times a vector gave us a vector. Dot product. We talked about this last time, so it's fresh. We remember all these things. What can we do? Well, it's useful for finding the angle between vectors because the dot product relates to the cosine of theta. Theta is the angle between the vectors. So that gives us a way to test orthogonality. So two vectors are orthogonal if their dot product is 0. We like orthogonal things. One of the things that comes with orthogonality is right angles. One of the things that comes with right angles is minimizing distances. Almost every time you are asked to minimize the distance, geometrically you should say, oh, a right angle is involved, which means that there's a perpendicular thing. We can also do projection. And in other words, how much of one vector points in the direction of the other. How does it work? Well, a vector dot a vector produces a number. Okay, so vector dot vector number. The last one we are talking about today is the cross product. And I already mentioned this. I'll say it a couple times because we want to make sure you remember this. The cross product makes perpendicular vectors. So if you're ever asked, I need to find something which is perpendicular, you're like, ooh, I know what I need. I need a cross product. Now you might be nervous and say, but wait, I thought it only works in dimension 3. The good news, we're going to work in dimension 3. We live in dimension 3. Our applications are dimension 3 based. And so it's going to be very useful. So anytime you're asked to find something that's perpendicular or something that's orthogonal, you should always think cross product. And it has a nice magnitude. And more or less, these two ideas define the cross product. Here's an example. And you might look at this and say 215 cross negative 312, negative 3, negative 19.5. Of course it is. What? No, it doesn't make any. Why? Huh? We'll explain. We'll explain. All right, so those are our 3 different vector products. All of them have uses. They will all continue to show up for the rest of the semester, especially towards the end. We're going to get towards the end of the semester. We're going to be using all of these. All right, any questions about our vector products? This is our little Cliff's note. Okay. So, doing a sort of a quick, huge amount of data dumping here. Like they're just going to throw a lot at you. So let's talk about the cross product. We have some goals. Whenever we have a vector, we think about how do we describe it. There are 2 inherent things. There's direction and there's magnitude. If we understand both aspects, we've got the vector. So let's start with our direction. So this goes back to our 2 plus 1 equals 3. We have 2 vectors coming in. So I have vectors u and v. So let's go ahead and put them together. And if I have 2 vectors, and I'm going to assume they're not parallel. Parallel vectors are not interesting with the cross product. We'll go over that in a second. But if I have these 2 vectors which aren't parallel, and I put their tails together, they are sitting in a plane. There's a unique plane that contains these 2 vectors. Now, you might not be as comfortable with plane yet, but you will become next lecture. But the idea of plane is your flat object. Just think of it as a piece of paper. Nice, flat object. 2-dimensional. And so, those vectors form this sort of 2-dimensional shape. Your third direction that you can identify is, let's take something perpendicular to this plane. So our goal is to say, hey, we want u cross v to be perpendicular to u cross v to be perpendicular to v. So there's some direction that is perpendicular to that plane. But there's a catch. Which way do we go? If I have a plane, I want to be perpendicular, I could be going up or down. Like imagine the xy plane. You could be going up the positive z-axis or down the negative z-axis. We have to have a way to be consistent and to choose. So there's a tiebreaker. And that's your right-hand rule. Don't stress too much about this, but I just want to explain what it is that's defining our rules. So in case you're wondering what the right-handed rule is, you start with the right hand. So most of you hopefully have one conveniently nearby. If not, talk to your neighbor, ask their permission before you use their right hand. But okay, so you start with the right hand. Now, it turns out your hand has this little bendy part. Mine doesn't bend quite as well as yours, but it bends really well one way. It does not bend really well that way. If it does, go see the doctor. All right, so here's the idea. You're going to take this portion is your first vector. That's your U. That's your fingers. The palm is your V. And you're going to put them in a way where you can actually close it up. So in other words, the angle has to be in acute, well, I shouldn't say acute, less than 180. So here I have U and V, so I put the U and the V. You close your hand up, wherever your thumb is pointing, that's the direction. So if I take U cross V, should I be going up or down in this illustration? Going up. Going up, up, up. Sorry, I've been watching too much K-pop Demon Hunters. You know, I've got that song in my head. Up, up. I can't hit the high notes yet. Not yet. Okay. But someday, maybe. All right. So, that's U cross V. What happens if you switch? Instead of U cross V, V cross U, what do? You go down. You go in the opposite way. So we have this sort of strange thing where now, if you look at U cross V and V cross U, they actually differ. They're not the same. So order matters a little bit, only up to a minus sign. And that's just because of the way you have to break your tie. One other thing to note is that U cross U equals 0. There's a couple of ways to think about this. One way is to think about this is you say, well, U cross U is the same as U cross U, right? Because but it's also the same as negative U cross U. And the only vector that is equal to the negative of itself is the 0 vector. Now, all right, that's a little bit hand-wavy. But another way to think about it is if I start with U and U, I don't have two directions to begin with. I only have one direction, and that's not enough. Okay, the other thing is we'll just come out and say we want our magnitude to satisfy this. So we'll say our magnitude of U cross V is magnitude of U, magnitude of V sine theta. And we also want to distribute. So U cross V plus W is U cross V plus U cross W. This is just a fun way of saying, hey, you know what? We want to FOIL. So that's our real goal. And that's something we're going to do in just a moment. That gives us our formula. So once you can distribute, you can FOIL. And the other thing you can do is you can pull out constants. So if I scale a vector, the result will be scaled. So if I have K times U, and I cross that with L times V, I can pull out the K and the L. And just say U cross V times KL. One of the things this allows us to do is if we're working with vectors, we say, well, all of our entries have common factors. Pull out the common factor. And just say, look, I'll multiply the end result when I need to. And it just makes things a little bit simpler. All right, with all this in mind, we have our vectors I, J, and K that we talked about when we talked about vectors. I points in the X direction, J points in the Y direction, and K points in the Z direction. And now you just go through and you just say, okay, if I take a vector cross itself, I get 0. So I cross I is 0, j cross j is 0, k cross k is 0. And then for the other ones, you note that all the angles are right angles. Sine of a right angle, what's that? It's 1. And the vectors we started with are 1. So it says the magnitude of any of these products has to be 1. So it's just purely direction. And you just start going crazy with your right hand rule. So, you put I on the x-axis, j on the y-axis, k goes straight up. So I cross j equals k. And you just work it out and play around. And you get this collection. Once you have what's on here, everything else is forced about the cross product. There's no additional things. These are our basic assumptions, our basic building blocks. All right, are we ready to actually make the formula? Okay, spoiler alert, we're going to do this. Okay, so don't panic when I put this down. There's this little piece of advice down here. Don't memorize this formula. We're going to talk about a better way to do this. But I want to show you that the formula follows from what we've talked about. So what happens? Well, if I start with two vectors, A, B, C, D, E, F, I think about that in terms of I, J's, and K's. So I rewrite them. AI plus B times J plus CK. And I take the cross product. Now I can distribute. In other words, I can do what FOIL does. Except I don't do FOIL because there's more than two terms in this expression. I take everything from the first combined with everything from the second. I'm going to end up with 9 possibilities. So things like I have A times I. Whoops. That should have been a D. There we go. A times I and D times I. And I cross those. AD, I cross I. And I'm just glad I only messed up on that one term. I hope. Yeah, good. Everything else is fine. So you go through. This is not exciting, but you have all these individual combinations of cross products, and you say, "Oh, wait a second. We already talked about these. Use your right hand rule, or use the fact that something crossed with itself is 0, and you can replace everything without cross products." And so you do that. And then you say, okay, now you gather things. So for example, for the first coordinate, which is the I coordinate, you have B times F and a minus C times E. For the J, you have a CD and a minus AF. And for the K, you have AE minus BD. So that's the formula. So it's forced on you once you make assumptions about, I need there to be this rule about the direction. I need to have my magnitude satisfy this property, and I need to be able to distribute and pull out constants. Then there's only one way to do it. And this way does it. Now, this is not how to remember the cross product. Let's talk about how we remember the cross product. So, use a determinant. There had to be a reason they made us learn all this in algebra, right? We had to talk about matrices, 2 by 2, 3 by 3. It's finally paying off. So I'm copying the formula down from the previous page. So this is the cross product. That's the formula that it has to be based on our assumptions we made. So let's go through. We'll do it in parallel. So there's a few basic steps. So it says step 1, you're going to write down a 3 by 3 matrix. So how do you do it? Well, the first row, you put I, J, and K. And those stand for I, J, and K. So those are vectors in the first row. I know it sounds weird, but we're allowed to do this. Then you say, okay, go to the first vector in the cross product and write that down in the second row. Those coefficients, 3, 1, negative 2. And then in the second vector in the cross product, so that's 5, 4, negative 1, you put that down, 5, 4, negative 1. All right, that's your step 1. Put that matrix down. Now we go to step 2. Step 2 is to take the determinant. So how do you do it? Now here's how I do this. And there are different strategies. Some people like to do cofactor expansion. I just think for 3 by 3, I remember to take the diagonals. So I'm going to do the diagonals going down. I'm going to do diagonals going up. When I talk about diagonals, if I hit a wall, I go to the other side. So I'll go through it by example. So let's do the going downs first. I, 1, negative 1. And I multiply those entries together. I times 1 times negative 1, negative I. J times minus 2 times 5. J times minus 2. See, I hit the wall, wrap around, 5. Negative 10J. K times 3 times 4. 12K. Now, if we were doing it over here, in general, you'd have that I times B times F, so that's BFI. J times C, wrap around to D, so that's plus C times D times J. K times A times E, so that's A, E, K. So those are the downhill diagonals. Round 2, uphill. So, switch to a different color. Now you just do the same thing going up. 5 times 1 times K. Well, so the product is 5K, but now here's the trick. The downs you add, the uphills you subtract. So we're going to subtract 5K. 4 times negative 2 times I. 4, negative 2I. So it'll be negative 8I, and we're going to subtract negative 8I, which becomes positive 8I, as somebody mentioned. Negative 1 times 3 times J. Be minus 3J, and subtract it. All right, so over here, B, D, K. And I just like to do my bookkeeping where I put the I's on top of each other, the J's on top of each other, the K's on top of each other. Then we have E, C, and I. And so that's minus C, E, I. And then we have F, A, and J. So that's A, F, and J. So that's how you can take the determinant of a 3 by 3. It's really quite nice. Things get a lot more complicated for 4 by 4 determinants, but we're not doing those. Huzzah! Okay, we're not quite out of the woods yet, but we're almost there. So we took our determinant. The last thing is to gather terms. So in the first entry, those are your I terms. Minus I, and then minus minus makes a plus 8I. Altogether gives us 7. Minus 10, minus minus 3, negative 7. 12 minus 5, 7. And down here, what would you get? You get BF minus CE, right? The BF minus CE, the CD minus AF, good, and the AE minus BD. And if you check, the formula that we got on the previous matches this one. So we'll always produce the right answer. On a side note, this is a case where we have a common factor, so it might be easier to work by pulling out a 7. Okay, now an important question. We get to this point, and we're like, oh, I'm a little bit nervous. Lots of things had to happen. One little mistake could derail me. Is there a way that we can check our answer? As the great math philosophers have said, you should check yourself before you wreck yourself. So, how can we check? Why dot product? Yeah. Remember, our goal, one of the reasons we talk about the cross product is it makes orthogonal vectors. So we also have a way to test if something is orthogonal. So what we can do is say, let's test if we're orthogonal. I don't need to worry about the 7, because that's just going to scale. So we do a quick dot product, because that's faster than doing all the work again. 3 minus 1 minus 2 gives 0. That's good. We like 0 in this case. 5 minus 4 minus 1, 0. So, if you get your answer and they're perpendicular to both of what you started with, 95% of the time you made an error. You made no errors. You got it right. If you didn't get 0, 100% of the time you got it wrong. There's really, really a rare, small opportunity that the dot products are both 0 and you got the wrong answer, but it's basically very, very hard. Multiple errors had to work out and cancel. All right, any questions? Yes?
Would it be enough if we check to see if it was correct by checking the magnitude with sine?
Well, but then you have to find sine theta. So checking the sine theta can be hard, because then it's like, well, how do I find sine theta? Well, you can find cosine theta. Once you have cosine theta from the dot product, you can find sine theta, but that's a lot of work. Yeah. So we almost never check the magnitude part. We always test for orthogonality. All right, so punchline. A main use of the cross product is forming perpendicular vectors. Here's a problem. Find a vector which is perpendicular to both 4, -1, 3, and 2, -2, 5. What do we do with this? What was it?
1, -14, -6.
1, -14, -6. Cool. How did you find it? The cross product, right. All right. Anybody get the same answer? 1, -14, -6? Yes, good. This is a positive sign. A cross product will be involved in the next exam. I don't know how, but it will. So make sure you can do it. Do we need to go through and work it out, or I think we're good? Okay, so let's move to the next one, which is to say, hey, we can also use cross product for geometrical measurements. And that's dealing with the magnitude side. Now, the majority of the time when we use cross product, we're going to be using it for its direction properties, for making perpendicular things. But we can also, in a few cases, and this will happen, use it for its magnitude properties. So we said the magnitude of u cross v is the magnitude of u of magnitude of v sine theta. So how does that help us? Well, what we can do is we can form the following shape. A parallelogram, which I didn't do a great job of, but imagine I could draw accurately. So a parallelogram just means parallel sides. So I have these two sides are parallel to each other, and these two sides are meant to be parallel to each other, slightly off, but imagine I could have drawn it correctly. You can think of a parallelogram as being formed by two vectors. So go to a corner and have two vectors coming out. The vector on the bottom side matches the one on the top. The vector on the left side matches the vector on the right. And we say, well, since I'm in this corner, there's an angle between these two vectors. All right. Well, what can we do? We can talk about the area of a parallelogram. I don't know why it's so hard to say parallelogram. It's going to get worse in the next slide. So the area, how much area is there in this shape? Well, turns out if we want area, you need to multiply two things. The base, and we can find the base by using this part down here, the length of the bottom side. So that's the magnitude of one of our vectors. Then there's the height. So, okay, how do you find the height? Well, the way we can do it is we can drop down. And we look at this and we say, all right, well, we have a nice triangle, and it's not the wrong kind of triangle, it's the right kind. All right. And we look at this and say, well, we know the angle, we know the length of the hypotenuse is the magnitude of this vector, and we want the opposite length, because this length is the height. What relates opposite and hypotenuse? Sine. So the height is the magnitude of u sine theta. So that's where this term comes from. And we say, whoa, what? As if it was meant to be. The magnitude of the cross product is showing up. So if you're after the area of a parallelogram, you say, find the vectors that make its side. Take the cross product and take the magnitude. Now you might be thinking there and sitting and saying, I have an idea. What if I don't take the whole thing? What if I cut it in half? So in other words, instead of the whole parallelogram, we cover it up. Now we don't have a parallelogram. What do we have? Triangle. So a triangle is half of a parallelogram. So if I want to find how much area there is in a triangle, what's the goal? Find how much area there is in the parallelogram and divide by 2. All right, so find the area of the triangle where we tell you the vertices. So what's the game plan? I mean, we kind of have some clues. We have an area of a triangle up here, and here's an area of a triangle. So what do you need to do? Take a cross product. Now, we have 3. Which 2 do we take the cross product of? Ha ha ha! Trick question! What are these? They're points. When you do cross products, what do you need? Vectors. You can't take cross products of points. You can take cross products of vectors. So, what do you need to make? Vectors. So how do you make vectors? You pick a corner. Which is the correct corner?
Yes.
Yes! That is the right answer. You've mastered this. This is a correct corner, but this is one. This is one. You pick one. Doesn't matter. Once you've picked one, find the vectors. Say, okay, -2, 0, -1 to 0, -2, 1. It doesn't matter which order you go. Say, okay, change of 2 in x, change of -2 in y, and a change of +2 in z. That's the first vector. And you say, do it again. -2 to 1, that's a change of 3. 0 to -1, down by 1. -1 to -2, down by 1. Now we have 2 vectors. What do? Cross product, magnitude times a half equals the answer. And we'll skip that because I do want to spend at least 30 seconds with the last idea. Okay, so given how much I struggled with saying parallelogram, now I'll struggle with saying parallelepiped. Parallelepiped, 3D box. So, what do we want? We want to find the volume. And we say, look, there are 3 vectors. There's a vector going in one set of directions, another vector going in a second set of directions, and another vector going in a third set of directions. How do you find volume? Base times height. Well, we know how to find the base because it's a parallelogram, so that's a cross product. How do you find the height? Well, here's the fun fact. I see a right angle, so I want something perpendicular to the base. What's something that's perpendicular to the base? Well, I need to be perpendicular to u, and I have to be perpendicular to v. Do we know anything perpendicular to u and v at the same time? The cross product. So this direction, this is in the direction of u cross v. So now we have the direction. We say, all right, find this angle, and we want the adjacent side. Well, that's a cosine. So it's magnitude of w times cosine. Well, what involves cosine? Dot is something you should remember. Dot product. So that's how we end up with a w dot u cross v. And here's the fun thing. Last thing I'll say. How do you actually do it? Once you have your three vectors, put vector 1 in the first row, vector 2 in the second row, vector 3 in the third row. You take your determinant. That's the volume. Determinants are volumes. All right, that's it. We'll pick up again next time.